All right, good morning, everybody. So we've got a few things to get started here. So for starters, we've reached a point where I just kind of have to release the survey results. No one is doing them, but I have to release the survey results so that you can start working on your survey project, right? So I will release those later today. Let me write that down. Release survey. So remember to do it right after class. So I'll release those survey results. You will have a link to the data, and then it will open in StatCrunch, and you can do the things that you need to do in StatCrunch. Next time we'll take a little bit of a look at it, and I'll discuss what some of you might want to do with your data. So some of you are going to have to fix your data, stuff like that. In fact, maybe we'll spend a little bit of time today going over that so that you can get started on that right away. I've never had a class do so few of the surveys. This is by far the lowest number of completed. This is the smallest sample size I've ever had for a class. It's not the smallest class by far. We're almost a full class, but it's the smallest number of people that have actually taken the survey. So I guess it would seem like people couldn't be bothered to take the survey. It's just your stuff's going to be harder to work on because your sample size is so small. Your histograms aren't going to look as good. It's going to be harder to tell the shape of the histogram because you have such a small N. So it's unfortunate we could not get more people to take the survey. I'm going to have to figure out something else next time because apparently people are only going to take the survey if they're getting points for it or something. So instead of just being able to do the thing that helps us all move forward. So I guess I'm going to have to do a thing in the future where there's screenshots of you finishing the survey or something like that in order to get points. It's kind of disappointing that we couldn't pull that together, but it is what it is, and that's what we have to work with. So to those of you who completed the survey, good job, right? Very good job. Give yourself a pat on the back. You didn't get points for it, but you did a good thing for the group, even if you're not being rewarded for it. Right. Other thing I wanted to mention was the school has changed its I think I forgot to mention this on Monday. So the school has changed its policy. Remember how even though I'm teaching 100% online, I had to do 3 of my office hours on campus according to school policy? Well, the union and the school have worked it out, and I no longer need to do that, which makes more sense because I only had, I think, 4 people show up to my Monday office hours. Even though that's 60% of my office hours, it was the fewest visited, and that makes sense because people who take an online class probably aren't going to feel like going to campus, getting through a screening process for COVID, finding my office, and then talking to me. So there was a handful of people that were willing to do that. But in general, I think it makes more sense since I'm teaching 100% online. My office hours would be 100% online, and that's how they are now. So my Monday office hours that take place from 11 to 2 will now be taking place in Zoom. So please come see me if you need help, right? If you're confused or you have questions or you don't understand how to do something, come to those Monday office hours and I can help you, right? And it doesn't even have to be like a big thing, right? I have other people in my other stats class. They're coming and they're like, here's what we think we're supposed to do for this part of the project. Is that right? And then I look at their work and go, oh yeah, this is pretty good. Here's a couple things you might do differently. Do you understand why I'm saying to do it this way? And they, oh yeah, I see what you're saying. That's better. That's right. And they kind of go from there. So we sort of can unleash things so that you can, and I'll go over it. And like I say, I'll go over it a little bit this time. You can start actually, I should wait until I have that data released. We'll go over it next time. I'll release the data for before class next time. So actually, I'll release it on Monday, and then I'll talk about it because it's actually going to hold you back if you get in there and you're trying to do stuff with it that you don't know how to do yet. So I'll release it on Monday and then talk about it so that you understand how to use the data, all that kind of stuff. So that'll be Monday's class. So Monday, discuss survey data results. Okay. So Right. So come see me on Monday office hours if you need help, 11 to 2 Mondays. Okay. So let's see. So that should put us up to correlation and regression is what we're talking about now. So that's to do. You have a little bit of time to do that, but it's coming up, right? So remember, hopefully you're largely through with chapter 3. Chapter 3 is not too bad. Should be able to move through it relatively quickly. Starting next week, I'll change the dates for these survey assignments, these survey discussions that you'll have to do. And then over here, we're getting into scatter diagrams and correlation. So correlation is hugely important. Let me move that in statistics, right? And it not only as a tool that we're going to use, but also as a concept. There's all these concepts in statistics that, students are good at memorizing formulas and procedures, but they're not always good at understanding what they're actually doing, right? What are you actually doing when you run a hypothesis test? This is one reason I've gone project-based. Part of the reason I've gone project-based is because we're online, and trying to test a math class online without any kind of proctoring software is ridiculous. Like what we saw, in many classes, just unprecedented levels of cheating when you have a test, because there's all these apps that help you cheat. It's harder to do that on a project because you have to build your own project. That's part of it. But also part of it is, we see in these stats class students who can memorize how to do certain things. And then, they'll say, well, here's my hypothesis test, and my p-value came in below the cutoff value, and so I'm going to reject the null, and here's my conclusion, right? And then you go, okay, can you just explain to me in words, like just normal language, what your conclusion is then? And they go, no, I don't really know, but I know that I know my p-value is small, and so I reject the null. Like they memorize the procedure, but they don't actually have any idea what they're doing. Okay, that's not really learning. That's an indication that that whatever your knowledge is easily replaced by a computer algorithm, which is what you don't want going forward, right? You want to be in a position where you are hard to replace by a computer algorithm. And that's really where the understanding comes in. Especially, like, think about StatCrunch. We can do all the actual calculations that we need on StatCrunch. The thing that's interesting is being able to know what it means for your business or your research or whatever it is that you're trying to use statistics for. Those conclusions are the important thing. And a lot of these topics, there's these underlying subtleties in statistics which makes it kind of hard to actually make good conclusions, right? And good conclusions are one of the things that makes an A project, not just presenting to me what you saw, but telling me like what it means, making conclusions, that kind of stuff. That's what kind of bumps a project up to an A, is that all the other stuff is done well. And then on top of that, they're showing that they understand what the conclusions are that we can conclude from the statistical work, right? And correlation is one that confuses people a lot, right? People who don't know statistics completely mess it up. And then people who know statistics a little bit tend to mess it up a lot too. So what we want to do is get to a point where you understand correlation and what that means, and that you don't get sucked into these false or misleading conclusions that get made. Okay, we see this literally right now in the news with politics and COVID-19 vaccine mandates and all sorts of stuff. You're hearing people throw around numbers. Like it's maddening right now to listen to the radio as someone or the news as someone who actually knows how statistics works. It's absolutely maddening to listen to people talk about statistics and then make a completely wrong conclusion. But it makes sense to them because they don't know any statistics. Right? It's like a lot of things. I could go into a subject and say something that makes sense to me that I don't know what I'm talking about because I don't know what I'm talking about, right? So that's hopefully one of the goals when you leave this class, is that when you're listening to the news or your politicians making a claim, or a business who wants to sell you a product making a claim, you can listen to it and go, yeah, you were pretty good up until your conclusion, which is like completely backwards from what it's supposed to be, right? That's one of the skills that I hope you take away, because the truth is only a limited number of you are actually going to use statistics on the job in the future. But you can have being able to go forward and have a good understanding of statistics so that when someone is trying to pull the wool over your eyes, or when they, you can identify that person's trying to trick me because they want me to buy a product, or that person's trying to trick me because they want my vote, or that person is trying to mislead me because they're trying to sway public opinion or whatever. Like, you will have that skill to recognize when someone throws statistics at you and it makes sense, because that's actually a technique people use. And as someone who has a PhD in math, and most of my colleagues I think would agree, you can take control of a lot of situations by going into them, and you just start talking about some statistics, and everyone sort of, their eyes glaze over and go, I don't know, this guy sounds like he knows what he's talking about. I'm just gonna go with whatever he says, right? But that's not really what you want, right? You don't want to be one of those people that's getting convinced because statistics are getting thrown around. You want to be able to go, I'm not sure if he actually knows the statistics that he's talking about. That doesn't sound right to me, right? You want to have that level of ability so you can decide for yourself. And correlation is a big one. This is one of the biggest mistakes that gets made in statistics, because statistics can almost never show cause and effect. But people, when they talk about statistics, almost always want to imply cause and effect. You'll hear this all the time, right? They talk about the connection between two events. Therefore, the first event must have caused the second event. And it's almost always wrong, right? Very rarely in real life do we study statistics with something where you have A causes B, end of story. Because the reality is, if the connection is that strong, then we don't really need statistics to study it, right? Like, like basic stuff. If I don't feed my dog a meal, he's going to be hungry, right? That's pretty clear. The cause is that I didn't put food in his bowl, and the effect is that he's hungry. We don't need statistics to study that. It's pretty straightforward. There was a cause, an event. I didn't feed my dog. The effect, he was hungry, right? It's pretty straightforward. When you start looking at things in life that are more complicated than that, economics and science and business, where there's lots of moving parts, very rarely does one single cause make one single event, right? There's lots of things involved. Like we're approaching, because of many decisions we've made in the past and ongoing, it looks like we're about to enter an economic downturn. You're going to hear lots of people claiming this is the reason why there was a downturn and it's this person's fault. Well, if you sit down with economists, they're not going to say, yeah, this one thing caused the economy to fall. They're going to say, well, there was the way that the Fed has been handling interest rates for years and years and years, and it sort of came to the end of being able to do that. We have the COVID is affecting things greatly. We also have the fact that people are getting tired of the income inequality, and people aren't willing to work for wages that don't actually allow them to survive. There's lots of causes that are that are leading up to this economic downturn, and the truth is there's plenty of blame to go around to lots of people. So, that's the kind of thing you want to be look at, because you're going to hear this one thing is the reason the economy's bad. So vote for this person or don't vote for this other person. But it's way more complicated than that. There's a whole bunch of reasons why we're about to have an economic downturn, right? So you want to be able to listen to the statistics and say, yeah, I see how that's part of the problem. The thing you're talking about is part of it. Because that's the arguments you're going to hear, is people on both sides arguing, well, it's this one thing that the other side did that caused the economy to go down. That would be cause and effect. Really what it is a bunch of events have occurred, all of it affecting the upcoming downturn. And but that doesn't make good television, right? That doesn't make good sound bites. So people don't argue on an actual intellectual level. They just sort of throw arguments at each other. You want to be able to move past that, right? So with correlation, what we see is that two things may be related, and one might partially cause the other, but we can only kind of get it. We can get into that a little bit with statistics, but again, you almost never in statistics are able to say A 100% causes B. We will be able to say things like, well, we think that 30% of this one thing is caused by this event, or 40% of this outcome was caused by this initial action. You can sometimes do that, right? But usually there's numerous things going on. And sometimes what you'll see is connections that are not cause and effect at all, right? And that's where correlation comes into play. And most of the time when you're dealing with statistics, you're dealing with correlation. So for instance, there's some famous examples for correlation, and I may have mentioned them earlier in the semester, but we'll talk about them again because they sort of point out what I'm getting at. So you can draw a very strong connection between ice cream sales and shark attacks, right? That's sort of, there's a handful of famous problems that get talked about that really show this. Very strong correlation between ice cream sales and shark attacks. If you graph both of those, you're going to see when one goes up, so does the other. When one goes down, so does the other. Well, no one's about to say, well, we better outlaw ice cream sales because we don't want people being attacked by sharks, right? So what you're noticing there is you're noticing two variables that are closely related, shark attack data and ice cream sale data. And you're saying, well, they really do the same thing. But it would be ridiculous for us to think that one causes the other, right? If you are bit by a shark, that does not cause you to go eat ice cream. And if you eat ice cream, that doesn't make you tastier for the shark, so they come bite you. The reason that those two variables change together is that they both happen in warm weather, and they rarely happen in cold weather, because when it's hot, people buy ice cream. When it's hot, people go in the ocean. When it's cold, people buy much less ice cream. When it's cold, people don't go in the ocean. If you don't go in the ocean, it's really hard to get attacked by a shark, right? So you see how in that case it would be really ridiculous to make a cause and effect claim, even though you can get a really strong correlation. So you don't want to get into that idea of thinking that just because two things have a strong correlation, that must mean one causes the other, right? Another famous one is that the more automobiles that you own, the higher your life expectancy is. Yes, if we track those variables, the more automobiles that you own, the longer that you are expected to live. Does that mean that buying a vehicle causes you to live longer? No, that would be ridiculous, right? I'm going to go buy 5 cars then. I'm going to live like super long. No, that's ridiculous. The connection there, so this case shows, and the last one does too, what we call a hidden variable or a confounding variable. That is a variable in play that affects the two variables you're looking at, but is not in your discussion. So the confounding variable in our last example was the temperature, right? The temperature affects both ice cream sales and shark attacks, but it doesn't mean that one of those things causes the other. The number of automobiles you own and your life expectancy is largely a function of how much money you have. What is your personal wealth? People who have more personal wealth have more automobiles. People have more personal wealth have better health care, which leads to a longer life expectancy, right? So, but we cannot connect those variables in a cause and effect way. You can say, we think they're both affected by wealth. And if you did some more advanced tools, you could start to say, yeah, we think wealth plays this much of a role in both of these two variables. But again, you could not, you're not really going to be able to make a direct cause and effect because there's multiple things causing life expectancy, right? It's not just one single thing. It's not like if you have enough money, you can live forever. Not yet. There's more stuff going on. So let's take a look in the book here. We've got correlation. One of the things we're going to be able to look at is, think of it this way. Here's another sort of example that gives us some insight into how correlation works, is that we can find a correlation between, like here they're asking about like crime scenes. If you're at a crime scene and we see some footprint evidence, from that, can we estimate how tall someone is? Well, we do kind of get the sense that in general, taller people have larger feet, right? You go, okay, I think, yeah, that makes sense. By and large, when we look at, basketball players who are like the tallest players, for the most part in society, also tend to have really big shoe sizes, right? And when you see someone who is noticeably shorter than average, they probably also have smaller shoe size. But does that mean that we can, how accurately can we predict height from shoe size? If I see a shoe size at a crime scene, can I then definitively say this person is 5'10" for sure? Right? That's the kind of questions we want to know. How tightly are these two variables connected? And can we make predictions given one of these data values? Can we make predictions about the other one? And if so, how sure are we that our prediction is right? Right? So can I just say, yeah, we saw a shoe print and we know the suspect then must be 5'10"? Or is it more like, well, with this given shoe size, we think maybe the person's between 5'8" and 6 foot, right? You might have to make that kind of an argument. So there's a correlation here, but it's not perfect, right? You can definitely find two people, like I'm sure we would have countless cases in this class. You find two people where one person is taller but has smaller feet than the shorter person that you paired them with, right? In other words, it doesn't hold 100% of the time. It's not a perfect line where, given your shoe size, we can predict your height. Okay, but there's a correlation where we can estimate your height and say there's a good chance it falls between these two values, but the ability to say, nope, we 100% know this person must be 5'10" because of their shoe size, probably not, right? But it can be helpful to get that estimate in there. So we have this idea of correlation, and you know, this is another thing. These two variables are connected, but one does not cause the other. Having a big shoe print doesn't cause you to be tall. Being tall doesn't cause you to have a big shoe print. What are these both affected by? Well, there's a ton of genes in your body that affect the size of your body, right? So there's various genes that you have that are going to affect your shoe size and your height. So it's not just one thing that you know that's the cause, and then these are the effect. It's more complicated than that. All right, so let's get into the official definition now that we've kind of talked about it. Let's get into the official definition of correlation. I can make that a little bigger, I think. A correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. Notice the words cause and effect never showed up anywhere in that yellow box, and we haven't even finished reading it yet, but the words cause and effect do not show up in there. There is a natural tendency for humans to want to immediately, their brain goes to a cause and effect. You'll find yourself doing this in all likelihood when you're doing these problems, and you have to train yourself to go, nope, I'm making that mistake that most people make that don't know statistics. I have to train myself. There is not a cause and effect here. And I'll even, you know, on the videos, the projects, I'm sure I will see at least one video where someone says, therefore this causes this. And that's not good, because we're spending so much time talking about how this does not justify a cause and effect relationship. So try to understand it's more subtle than that. There's more nuance going on in this kind of a discussion. A linear correlation exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. That might sound confusing. We're going to look at a picture in a minute, and you're probably going to go, oh, I get what's going on. I see what's happening here. Okay, so we'll clear that up. But basically what it's saying is the relationship between these two variables, when graphed, makes a line. Okay, is basically what we're saying. And I thought there was am I thinking of a different part? I thought there was a little blue box here, but we'll have to go back to it. I guess not. I must be thinking of something that's on a later page. I thought it was right there. Okay, so let's look at a scatter plot. What is a scatter plot? Well, a scatter plot is when you plot two different quantitative variables at the same time. So remember, quantitative means you're counting a quantity, right? So they have to be numeric, and they have to be numeric in the way that you are counting something. This is why, for your questions, I strongly urged you to pick two questions that were quantitative. Because if you only have one quantitative question, then you can't make a scatter plot, because you need two. Right? That was the whole point of making sure you use two quantitative values, so you'd have enough to make a scatter plot. So hopefully you did that, and then you can make your scatter plot. So what you want to be able to do is see what they've done here. Shoe print along here in centimeters, and then height in centimeters here. So you can see there's kind of an overall behavior here, right? where, yeah, it looks like in general, people who have the smaller shoe prints are also shorter. And as we move to the right on the shoe print axis, we're also moving up on the height axis, so that in general, you see this overall behavior, but it's not bulletproof, right? Like, look at this value right here. What if we found someone who was, what is this, like 32 centimeters? And you say, well, if a person with 32 centimeter feet, this must be how tall they are. Well, look, we have 1, 2, 3, 4, 5 different measurements, all that are right around 32 centimeters. So you cannot definitively say, if someone has a shoe print of 32 centimeters, this is how tall they are. But what you could probably do is say, well, we would expect them to be somewhere around this point right here. And, you know, if you're doing that and the suspect that you're looking for has a height of 155 centimeters, then you might say, well, it's kind of unlikely that from our data that a person who's only 155 centimeters tall would have a shoe size this big. Does that mean it's impossible? No. But when you're talking statistics, you're generally talking probabilities, right? Which is what people fail to do when they bring statistics to the masses a lot of time, is they stop talking about probabilities and they start talking about assurances because they want you to buy something or they want to convince you of something. But we could say, yeah, there's a good chance that the person is between 175 and 185 centimeters from this shoe print. Is your suspect in that range? Yes. Okay, well, that doesn't prove the person's guilty, but it does indicate that we might be looking in the right direction, right? You don't know. And look at this. Even when you go down to, say, 31, you have some even taller people. So it's definitely possible that if you're 31 centimeters, you still might have that range in height. So it's not a perfect tool. You're not going to put anyone in prison with this kind of evidence. But if you put together 3 or 4 pieces of evidence and you say, well, yeah, they're not the right height, and then also, you know, they don't drive the right kind of car, like enough of this evidence that puts doubt in your brain, you start thinking, maybe we're looking at the wrong person. Maybe we need to get ourselves another suspect, right? But you have to use this in the right way. So here's how the scatter plots work. Now you might ask, how did they know to put shoe print down here and height up here? It just depends on how you're trying to make the connection, right? You think of this generally like back to algebra. This is your independent variable. This is the one you want to pick, and this is the outcome that you want, is generally how you're going to set that up. But you could do it the other way around, right? If you're trying to look for, you know, you're an investigator and you're trying to look for a suspect to a crime, you might not have their height. You might just have a shoe print. So in that case, you'd find where their shoe print is, and you'd look where those data values are and say, does my suspect have that height that is in those ranges? And that may or may not be a determination for you. What about the other way around? You might have the height and not the shoe size. How'd you get this? Well, right, we've all been in like stores where by the door they have that there's like a ruler on the side. The whole point of that is that when someone is fleeing the store, the camera will be able to see how tall the person is, right? If the criminal is running out the door and the top of their head is right next to the 6 marker, that means they're 6 feet tall. So in that case, the police might want to put height down here and shoe size up here, and then say, well, the person was 6 feet tall, and then look at the shoe size of their suspect and say, does it fall in the range that we would expect? Again, not proof that you are innocent or proof that you are guilty, but it is a piece of mounting evidence either for or against the case that you did it, right? So the answer is there is no right answer about should shoe size be the x-axis or the y-axis. It depends what you're doing, okay? Oops. Now, we can get lots of different scatter plots. We can get, as you can imagine, all different shapes, right? As you go out and you collect data and you do your scatter plots, you're going to get lots of different shapes to things. So one thing we want to look at is, what is this R that they're giving us? R is an extremely important idea. R is actually, R is the measurement we use to indicate how tightly connected 2 variables are. Okay, so for instance, see how this R value is at point, and it goes, I wish they would show this graph earlier. I'm going to show you this, and then we're going to go back. this down. Where's the chart I'm thinking of? Oh, is it in regression? Let me see if it's in here. Somehow I missed it. I don't know where that thing is that I was looking for. Somewhere in here there's a diagram that I was looking for, but I can't find it at the moment. So what happens is your R value can be anywhere from -1 to +1. Okay. Being close to -1 makes a strong negative correlation. Being close to +1 makes a strong positive correlation. Now, sometimes people think a negative correlation means things aren't correlated. So they'll get like this one here, -0.965. They'll go, oh, so that's a negative correlation. That means there's no correlation, right? No, there is actually a very strong correlation. In fact, this is the strongest correlation in the 4 graphs we're looking at. Negative is indicating the slope of the data. Right? Remember from algebra, you can have a positive slope if something's increasing or a negative slope if something's decreasing. The way this actually works, and I can't remember, I don't know why they're not showing somewhere in here is a chart that kind of clears up what I'm trying to describe to you. If your R value is near 0, that means there is very little connection between your data that you're looking at. That would be like this. See how the R value is 0? If I look at this and say, okay, given an X value, can you predict the Y value? You're like, no, because there's all over the place. There's no pattern to this. Like if I tried to get you to describe this pattern, what would you say? You're like, I don't know. It's just like, looks like someone spilled some coffee grounds on the floor or something. It's just like stuff's just everywhere. There's no pattern to it. That's what an R value of 0 indicates, is that you can't really use one variable to estimate the other one. Right? So it'd be like, things that are kind of related, shoe size and height. One of them kind of gives you a rough idea of the other one, but it's not very exact, is it? But if you took two things that seem totally unrelated, the number of trees on your property, and then how many times you go to the bank in a week, right? Those two things probably are not going to be correlated very, very much. You're going to see a pattern like this where they don't affect each other, all right? So that R value is near 0. So what do R values as they approach 1 and -1 mean? Well, see how this one's starting to get close to 1? Think about if you took this data and I said, draw a line through there that you think best fits the data. Well, you're not going to draw a line like this, right? You're going to draw a line that starts somewhere down here and kind of goes up through the data and then ends up over here. That's the line that goes through your data. Okay. We're going to use StatCrunch to come up with that line for us. So that's nice because it's with this many points, it'd be a huge calculation. StatCrunch is going to do it. But we want to be able to look at that line that goes through here because the line we're going to use for our predictions. Now, in this case, we're going to use the fact that R is only 0.851 to realize there can be a variation in here because we could take the shoe size data and take the line and predict, okay, this says the person is probably 5'10", but then we know, well, it's a bit of a loose correlation, so they're probably not exactly 5'10". They're probably between 5'9" and 5'11", or whatever it is that your correlation allows you to make some kind of a range. Notice how our data over here is even tighter. Like the line that you would draw through here is even more obvious, right? You'd start up here and go down here. So when we say negative correlation, all it means is the line we're drawing has a negative slope. So the R value is near -1, right? Negative, like I see this all the time. Negative correlation does not mean no correlation. It means that your correlation is high, but it's in a negative direction. If you were to draw a line through here, the slope would be negative because it's decreasing. So does that make more sense? Our data is a little tighter over here, so the data is a little closer to -1 than this one is to 1. If this had the same R value, 0.965, we would expect our data to be much tighter together like the one over here. Okay? So it's the closer you are to 0 is when you don't have a strong connection between those variables. This one, R value of 0, no connection. You can make no prediction at all. And think about it. If I asked you, can you draw a line through this data that accurately describes this data? No. Well, you could put one here, put one here, here. Like there's a bunch of lines in here, and you can't really argue that any one is better than the others, right? That's because there's no correlation. That R value is extremely important. Every time you talk about correlation, you should know what that R value is. The good news is StatCrunch is going to calculate it for you. All you have to do is press like 3 buttons and then look at it, right? Now what's going on over here? Well, remember we talked about linear correlation. This can be described with a line. This can be described with a line. Could this thing here be described with a line? No, that looks pretty clearly quadratic to me. So we could do quadratic regressions, exponential regressions, log regressions. Those are all the thing, and StatCrunch will do them for you, but we don't really address them in this class, right? For now, we're just trying to wrap our brains around linear regression, and once you do that, you kind of understand the rest of it to a pretty good degree. It's just that you realize it's a parabola, or it's a third-degree polynomial, or it's an exponential, or a logarithm, right? So, but here, clearly, I can't come up with a line that describes this data. If you came up, but here's the thing you have to realize. StatCrunch will give you one. If you take this data and you put it into StatCrunch and say, find my regression, it's probably going to give you a line that goes right through here. But that regression line would not give you good predictions, right? Sometimes it's going to come in, it's going to, like over here, it would be predicting values way too high. Imagine there's a red line right through here. Here it's going to be predicting values that are way too low or way too high. Here it would be predicting values way too low. And here it would be predicting values way too high. It's not really useful anywhere except for tiny parts right here and here. That's not a very good model if it's wrong like 80% of the time, right? We don't want to construct those. So this is what if you graph your data and you see something like this, don't try to fit a linear regression to it. You're going to have to fit a quadratic or cubic or something like that. Now, most of you are probably not going to get those cases for the kinds of questions that we're being asked in here, but that's what we mean when we talk about the non-linear correlation and linear correlation, okay? And here's that R value, right? The R value is so important that there's a programming language written specifically for statistics. So those of you, if there's anyone in the class who is thinking of studying statistics, which is not a bad idea. When you think about the jobs that are going to be replaced in your lifetimes, statistician will be around longer than a lot of other jobs. So not a bad idea to get yourself a stats degree, and generally you can make a fairly good income with a statistics degree. So if you at all think that statistics is interesting, I would encourage you. That would be a good choice for the future, because you'll have a good paying job, and it might even last you till retirement if you're good at it. Whereas every year lots of other jobs are being replaced and automated. So people who really know statistics, you learn this programming language called R. It's literally just the letter R, because that idea of R is so important in mathematics, or in statistics, I should say, that they named the whole programming language after it, right? So the linear correlation coefficient R measures the strength of its linear correlation between the paired quantitative data X and Y values in a sample. So in other words, you have two quantitative sets of data. You plot them on a scatter plot. You calculate the regression. This R value is going to come back, and it's going to tell you how strong your variables are connected to each other in a linear manner. They give you some formulas, but we're not going to calculate them by hand, so we don't have to worry about that. So just know your R value is telling you how those things are connected. We don't need that because we're not going to calculate these by hand, so we don't have to worry about that. And just be careful. The methods we're looking at apply to a linear correlation, right? If you conclude that there does not appear to be a linear correlation, there might be a quadratic or exponential or logarithm. You've only shown that there is not a linear correlation. That's what we're talking about here. That's what gets used more often, like most of the time in statistics. If you're talking about correlation, you're probably talking about linear correlation, but there are other cases where it's appropriate to talk about other types of correlation as well. Okay, so some properties of this R value. You need to understand the R value. When you look at, if I just hand you an R value, you should be able to make a prediction about, before I show you the scatter plot, you should be able to make a prediction about what you think that scatter plot's going to look like, roughly. So the R value is always between -1 and +1. If you're close to -1, you have a strong negative correlation. If you're close to +1, you have a strong positive correlation. If the closer you are to 0, the more likely that your variables don't have anything to do with each other, that there is no connection between those two. R doesn't change if you convert your variable values to a different scale, which is nice, right? We're probably not going to do that in this class, but you could if you wanted to. If you wanted to convert all your centimeter measurements to meter measurements, your R value is not going to change. That's convenient. The value of R is not affected by your choice of X or Y. What does that mean? Well, remember how I said before you can put shoes on the X-axis and height on the Y-axis? Or you could do it the other way, where you have height on the X-axis and shoes on the Y-axis. Your R value is not going to change depending on that choice, which is nice. It kind of makes sense, but it's nice that it doesn't change. R value measures the strength of a linear relationship. It is not designed to measure the strength of a relationship that is not linear, like that quadratic graph that we saw. Okay. R is very sensitive to outliers in the sense that a single outlier can dramatically affect its value. We're going to see a picture of that. So if this is why there's two things going on. You always need to look at your R value, but you always need to look at the scatter plot as well. Now, those are pretty easy because you're just going to have StatCrunch make you a picture, and you're going to get your line, and you're also going to get your R value. So it's not like it takes any extra work, but you should look at it. Decide from your R value if you think there's a strong connection, but also just look at the data. There are times when you can get an R value that is misleading, but by quickly looking at the data, you go, whoa, something's not right with my data here. This is all messed up. And then you can fix it, okay? But just watch out for just do both, right? Look at the graph, look at the R value. StatCrunch is not listed on here because this is an older version of this textbook, but it's going to do just like this. It's going to say R equals. It's going to give you your R value, okay, in the output. And we'll look at that next time. We don't have time today, but we'll look at that next time when we are in StatCrunch doing some stuff. For that, we don't need to calculate these by hand. You can see the calculations get a little bit messy doing them by hand, so you'd only ever want to do this for a sample size that was very, very small, but we don't even really need to do that anyways because we have StatCrunch doing it for us, but they're helping you understand what it is. Oh, here's the graph I was looking for. Finally found it. Okay. I don't know how I missed that before. Okay, so here's our range, and then that'll kind of finish us up for today. Here's our range from -1 to +1. All your R values have to fall between -1 and +1. If you get an R value of 1.75, you have done something very, very weird that is just sort of impossible. So it's a mistake. In other words, something has occurred that cannot occur. So your R value has to be between -1 and +1, and you can see here, now they've just come up with these arbitrary cutoffs, right? A lot of times in the stats class, we're going to use 5% as the cutoff, but you don't have to. It depends what you're doing. So this is just so they could make a diagram. That doesn't mean if you're ever dealing with an R value of 0.877, you go, well, it's just on the left of this line, so no correlation, right? Really, the idea is as you move closer to 0, your correlation diminishes. As you move closer to 1, your correlation increases. Now, yes, when it gets interesting is once you get up above like 0.8. I would even move this over a little bit. Above 0.8, that's still a pretty weak correlation, but there is some kind of correlation going on there. And the closer you to get a 1, that data is getting tighter and tighter. Remember that graph we saw where it was very clear where you would draw the line of best fit in there? Also the same over here. When you get close to -1, that term negative correlation throws people off because they start thinking that means there's no correlation. No, there is a very strong correlation near -1. It just has a negative slope that line has a negative slope. So you can see if you fall somewhere here in the middle, like if you get an R value of 0.7 or 0.59, or like this one, sample data, 0.591, yeah, probably not really much of a correlation there. I wouldn't really talk about connecting those variables. That's pretty weak. But once you start getting up around 0.8 or something, it's something to take a look at and decide, okay? So this picture, sort of understanding this, if you understand what we're looking at right now, then you understand the R value and at least some of the subtleties going on in the section. We can get into fancier stuff with the R squared, but we're not going to do too much with that right now. Basically, what you can do, the value of R squared is the proportion of the variation in Y that is explained by the linear relationship between X and Y. So in this case, they took a sample of shoe sizes and height, and they can say, well, about 66% of the person's height is explained by the shoe size, right? But that leaves, what, 34% that can be explained by other things. So that's not a very tight correlation. I wouldn't think, oh, we can perfectly estimate someone's height from their shoe size. No, that's kind of weak. You can only 66% of it can be explained with this variable. So you want to make sure you're doing that. Okay, real quick. Actually, where are we? We're not doing a hypothesis test, so we don't have to talk about any of that. Okay, let's just go back up here, and then we'll pick up next time. So real quick, a couple of things to close here. A couple of mistakes people make. Common error is to assume that correlation implies causality. Nope, doesn't. There's usually some kind of lurking variable or some other thing going on that explains that. So don't, when you're doing this, do not try to get into cause and effect. If you do that, you don't have the tools for that, and statistics barely has the tools for doing that sometimes. So it's just not a good idea. And they even say here in this blue box, know that correlation does not imply causality. Even if you have a very, very strong correlation, you cannot say that one thing causes the other. Okay. Another error arises with data based on averages. Averages express individual variation. So basically, if you have averages of stuff and you're trying to do this, it's going to mess stuff up. I don't think that'll really affect most of you. And then right. So then they're saying here that the third error people make is, because you can put the data in StatCrunch, it's going to give you a regression line. It's going to give you an R value. And people are like, okay, I did what I was supposed to do. I calculated a regression line. But if you look at it, you go, actually, our data is not linear. So why am I calculating a regression line? You shouldn't be, right? Make sure your data looks like it can be represented with a line. Okay, so we are going to leave off there. Next time, we're going to talk more about regression lines. So there's the regression line, line of best fit, least squares regression line. There's a whole bunch of different names it goes by. They're all roughly the same thing. So we are going to talk about that next time. And then also next time I will release the data for you and then show you what some of you need to do. Some of your data is, for heights, people might have said, they might have just given a number, and then other people might have put the word inches after it. Well, when you go to calculate data for that column, it's going to ignore where people put inches because those are words and it doesn't know how to take the mean of a word, right? So I'll show you your data. I'll show you how to access it, and then we will go over what you need to do in order to fix your data so that you can actually run, have StatCrunch crunch numbers for you. And it's really important, especially for this class, since very few people actually took the survey, that it's really important that you be able to use every single data point you can get your hands on, because your sample sizes are already sort of inappropriately small. This is a learning exercise, so it's not that big of a deal, but it's going to make the work a little harder to do. So anyone who still can get in there and take that thing, I'll leave it open, and then before our class on Monday, I'll get all that stuff ready, and then we'll move forward with it. Okay, because I'll have to show you how to use it in order for you to do the new assignments and stuff. Okay, So we will leave off there. Anyone who wants to talk to me in Zoom, please hop over to Zoom. I'll talk to you about whatever your concerns are. Otherwise, I will see you next week. Make sure you're getting those homework assignments done. You got a bunch of stuff due in the near future, so make sure you're working on that, okay? All right.